I'm Jonathan Stern. I'm a postdoc at Northwestern University, and I want to discuss this issue of pressure support in galaxy-scale halos. Okay, so my talk focuses on the volume filling phase in galaxy-scale halos, and we know for quite a while that this phase is expected to go through a transition, okay, when the halo masses crosses a threshold of something like 10 to the 12 solar masses. Okay, so when in low halo masses where the cooling times are short, okay, the volume filling phase is expected to be pretty chaotic, dominated by bulk flows. But as the halo mass grows and crosses a threshold, okay, cooling times become longer, and at some point, the volume filling phase is expected to be much more spherically symmetric, quasi-static, supported against gravity by thermal pressure. So I'm gonna address this question of pressure support in galaxy-scale halos in 4 different stages of increasing complexity. Okay, so I'll start by deriving the condition for pressure support based on analytic theory. Specifically, I'll analyze the stability of cooling flows. And I'll then test my analytic results using both idealized simulations of the circumgalactic medium and using the fire cosmological simulations. Okay? And and in this part, I'll also show my main result, and that is that the onset of pressure support in fire coincides with the transition between bursty star formation and steady star formation in the central galaxy. Okay? I'll just end my talk by quickly connecting my results to observations. I'll show that we might have already detected this transition using UV observations. Okay, so this is kind of the technical part. I'm using cooling flow solutions to derive the condition for pressure support. Cooling flows, okay, they're solutions to the steady state flow equations of gas which is radiatively cooling in a constant gravitational potential. Okay, these solutions were discussed a lot in the 70s and 80s, mainly in the context of gas and galaxy clusters. And these solutions are spherical solutions, so they're one-dimensional, but they're separated. You can broadly separate these solutions to 2 groups, divided by a critical inflow rate, which we call m dot crit. Basically, what happens is that if the inflow rate of the solution is lower than this critical value, okay, then the solution transitions from being pressure supported on halo scales to being angular momentum supported on galaxy scales. Okay, so you can see this here. So the black line is the solution. You can see that on halo scales, the temperature of the solution is something like the virial temperature. The Mach, so the flow is subsonic. The Mach number is lower than unity. Okay, because corrections to the hydrostatic equations of order Mach squared. Okay, this solution on halo scales is very close to being hydrostatic. Okay? But once the flow reaches, the scale where angular momentum becomes important, the flow kind of cools out, okay, and the Mach number goes to 0. Okay, so this kind of solution corresponds to a radial hot flow which smoothly transitions into a cool rotating flow. However, if the inflow rate is larger than this critical value, okay, then you get a sonic transition on halo scales in the flow. Okay, so what happens is that the flow, it's initially pressure supported, but on small scales, it goes through a sonic transition, it cools out and becomes supersonic. Okay, so there's a gap in support in these types of solutions between where it's pressure supported and angular momentum supported. Okay, so in these solutions, the flow kind of crashes supersonically on the galaxy, and in these solutions, the flow kind of joins the galaxy with a negligible vanishing radial velocity. Okay. And this critical inflow rate is just derived from the condition that the sonic radius equals the angular momentum radius. Okay, so in this, the cooling flow solution, which corresponds to this condition, gives you the difference between these 2 groups. So that's one-dimensional steady-state solutions. Okay, but how does that look in 3D simulations? So to test this in simulations, we use the idealized simulations of the CGM developed by Drummond Fielding during his PhD in Berkeley. So basically what these simulations do, they assume that the background potential is constant, in this case corresponding to a halo mass of 11.5 at redshift 0. We put gas which is initially hydrostatic. Okay, we give it a little bit of angular momentum, and we just let it radiatively cool. Okay, so if everything is kosher, okay, we expect the gas to form a cooling flow. Okay. Now, I set the initial conditions in a way that the inflow rate increases with time, okay, and it will cross this critical value at 6 gigayears. So let me just show you what happens. Okay, right, so this is a temperature map. This is a radial velocity. These are flow lines in the simulations. Okay, so let me show you this again, and I'll explain what you're seeing. Okay, so initially when the inflow rate is lower than critical value, you have a hot flow, a mild inflow. That's the cooling flow forming a cool ring. But once you cross the critical value, everything just collapses into a supersonic flow. Okay, you can see that the flow lines become very, very steep. Okay, so this kind of suggests that this condition that the inflow rate equals the critical value is the condition for pressure support in the halo gas. Okay, so if we compare these idealized simulations with the steady state solutions, so the simulations are dashed cyan lines and the solutions are black solid lines, you can see that in these regimes, the simulations and the steady state solutions are roughly the same, okay? A hot temperature which cools out at the angular momentum radius. But here they're very different, okay? In the simulations, we don't see this configuration where we have a hot gas above cool gas. The gas in the simulation is supersonic at all radii up to the radius which are close to the angular momentum. Okay, so the point of this exercise, okay, is mainly to derive this condition, inflow rate versus the critical inflow rate. Okay, what you see here is a calculation of this critical inflow rate as a function of halo mass. This is specifically for redshift 0 halos, but you can repeat this at any redshift. And we expect, if the inflow rate is lower than this critical value, we expect a pressure-supported cooling flow in the halo gas. If it's above this critical value, we expect the gas to be in free fall. So what's done here, it's compared to the inflow rate that you expect in baryon-complete halos, and you can see that these kind of curves intersect at a halo mass of 10 to the 12, and that's exactly what Birenbaum and Deckel derived. Okay, so this is essentially a different way to derive the condition for pressure support than derived by Yuval and Avishai. And this way kind of highlights different aspects of this transition. Okay, so the aspects I want you to notice, first, that this critical inflow rate is just the maximum accretion rate of the hot mode accretion, right? Because this hot cooling flow, that's hot mode accretion. And what I showed you that if the inflow rate is larger than this value, then you don't get hot accretion, you get cold accretion. Okay, so this is kind of a evaluation of the maximum accretion rate of the hot mode. Okay? Another thing to notice is that if halos are baryon depleted, as suggested by some simulations, okay, then you could have pressure support even in low mass halos. Okay, if they're baryon depleted such that the inflow rate is lower than in baryon complete, you might have pressure support. And another very important thing is that the m dot crit is set by conditions at the galaxy scale. Okay, so it's the comparison of the sonic radius to the angular momentum radius. Okay, so the correct calculation, the correct metallicity to use for calculation is actually the metallicity very, very close to the galaxy. Okay, in this case, we just use the metallicity in the ISM of the central galaxy. Okay, so that's the analytic theory, but now let's test this on the fire cosmological simulations. Okay. So first, I'll note that there's been a puzzle in the last several years in the fire zoom-in simulations, and that is all simulations above a specific mass essentially go in transition in the properties of the star formation rates. They're very bursty at high redshift, and they become pretty steady at low redshift. Okay, so the y-axis here is the instantaneous star formation rate divided by a running mean, and you can see that there was a very well-defined transition between bursty star formation rates and steady star formation. Okay, and this puzzle has until now not received a satisfactory explanation, especially to why this transition is so sharp. So I want to show that this is connected to the onset of pressure support in the halo. Okay, so how do we test our analytic theory using the fire simulations? Okay, so basically we took 4 fire simulations. 2 are what's called the standard fire simulations, which are run down to redshift 0 and have a halo mass of 10 to the 12. And 2 are what's called the massive fire simulations, which are run down to redshift 1 and have where they have a halo mass of something like 10 to the 12.5. Okay? So what we did is that we took each snapshot of the simulation and we calculated the inflow rate if the gas forms a cooling flow and compared that to the critical inflow rate. And we just marked by these x's where these two values, the cooling rate to the critical rate, where they're equal. Okay, so this is kind of the prediction according to our analytic theory where we expect the onset of pressure support in the fire cosmological simulations. Okay? And what's shown here on the right panels, okay, is just the pressure dispersion in a shell at 10% of the virial radius. Okay, what I show you here is that the pressure dispersion is very large before the onset of pressure support. Okay, so when you're looking at the fire simulation in different directions, okay, you're seeing very different pressure before the onset of pressure support. Okay, but once the cooling time becomes longer than the sound crossing time, you get the onset of pressure support. Okay, and the pressure essentially becomes uniform. Okay, so the pressure dispersion drops below unity. Okay, so this is at 10% of the virial radius, and there's a weaker effect at 50% of the virial radius, but the general behavior is the same. Okay, so you get high pressure dispersion before pressure support and low pressure dispersion after pressure support. Okay, so this kind of suggests, that this analytic prediction works in the fire cosmological simulation, and indeed, the volume filling phase in fire goes through a phase transition, okay, at this redshift. Okay, so now let's compare, this transition in the properties in the onset of pressure support with other properties of the simulation. So what I'm showing you here is the fraction of gas in the CGM, okay, in the inner CGM, which originated from a wind. Okay, so what you see here, if you look at this, right, you can see that initially, before the onset of pressure support, the CGM is 50% winds and only 50% IGM accretions, so it's 50-50. But after the onset of pressure support and some time passed, okay, the wind fraction essentially went to 0. Okay, so the outflows are confined, or they die out after the onset of pressure support. You can see this in all simulations. Okay, let's compare to the star formation rate. Okay, so the red line here, the red line here plots this pressure support indicator, the ratio of the cooling rate to critical rate. Once this ratio drops below unity, that's where we see the onset of pressure support. Okay, and you can see that it corresponds pretty well to where the star formation is bursty and where it transitions to being relatively steady. Okay. One last thing, the black hole. Okay, in these simulations, in the massive fire simulations, we track the growth of the black hole. Okay, we don't implement AGN feedback, but what has been shown in these simulations, right, is that the black hole accretion rate changes from being very weak, okay, and very choppy at high redshift, and then there's a sudden transition, okay, where the black hole accretion rate becomes much larger and much more steady. And again, this transition, at least in most simulations, okay, seems to correspond to the onset of pressure support in the halo. Okay, so last 2 minutes. Okay, so last thing, onset of pressure support in observations. Okay, so I just want to discuss, there's this very well-known dichotomy in O6 absorption between blue and red galaxies. Okay, so this is the result from the COAST Halos team. Okay, they looked at O6 absorption, roughly 100 kiloparsec from local galaxies, and they found very strong absorption in blue galaxies and weak or absent absorption around the red galaxies. Okay, so I showed in my 2018 paper that the O6 absorption around the blue galaxies is actually consistent with a gas which has a very low pressure. Okay, the line ratios and the line kinematics are consistent with gas which has a very low pressure compared to what you expect in a virialized halo. Okay, so the pressure here is only 3%. The pressure in these models is only 3% compared to what you expect in a virialized halo. So if this interpretation is correct, it kind of suggests that blue galaxies don't have a virialized halo. Okay, they're before the onset of pressure support. Okay, and then the lack of O6 in the red galaxies may suggest that in red galaxies, the CGM is already pressure supported. Okay, so I'll just summarize. Okay, so the main point is that I kind of reformulated the condition for pressure support using cooling flow theory. Okay, we identified the onset of pressure support in the fire cosmological simulation, and I showed that it coincides with the transition between bursty and steady star formation, coincides with a drop in the wind content of the CGM, and with the onset of growth of the central black hole. Okay, and I also show that the observed dichotomy in circumgalactic O6 is consistent with blue galaxies being before the onset of pressure support and red galaxies being after the onset of pressure support.
Thank you. Questions from younger folks, starting back there. Yeah. Yep.
So I'm interested how this explanation for bursty to steady star formation in black hole growth compares to the idea that it's all about the internal structure of the galaxy. I had thought maybe I was mistaken that as the galaxies are growing,
Yes, so another thing that's correlated with the onset of pressure support is the fact that the gas becomes much more disky, okay, and less chaotic after the onset of pressure support. So we haven't yet entangled what exactly the cause and effect here is. Okay, so I don't have a very good answer. My main point here is that none of this, right, this theory doesn't know anything about the galaxy. Okay, so this theory cannot kind of come, except the free parameters which are set by the galaxy, might be set by outflows. This theory cannot know anything about the structure of the galaxy. Yeah, so it knows about the halo mass, it knows about the gas metallicity. Okay, so there's several parameters which are set by the conditions prior to the onset of pressure support. But what exactly, causes what, that's still an open question.
Daisuke?
Yeah, so have you considered looking at the entropy? The entropy is a good quantity for assessing non-gravitational effects. If you have a lot of heating, then you generate entropy through cooling or heat, or actually heating. So you can think of the entropy threshold as a way of sort of reaching across the T-cool greater than pH threshold. So this is like a nice way of actually measuring the effect of heat.
Yeah, so what you get in these cooling flow solutions is that you get a very well-defined entropy profile. The entropy just scales linearly with radius. It's like a very well-defined prediction of these cooling flow solutions. And we indeed see that in the fire simulation. So after the onset of pressure support, you see like a linear entropy profile in the volume filling phase. Okay, so it's pretty, like the expectation for the entropy in the cooling flow solution is realized in fire. Okay, so no feedback, no heating. Just a cooling flow.
You don't see entropy core in the center.
After the cooling flow, no. So, right, the cooling flow reaches all the way down to the galaxy scale, where angular momentum. Yeah.
So we have to move on. Sorry, we're out of time. Let's thank this morning's speakers again.